To build the artificial intelligence systems that run today's world, you need an almost incomprehensible amount of computational power. For decades, the industry generated power following Moore's law. Engineers relentlessly shrank transistors, cramming them side by side onto a flat piece of silicon. But that path hit a physical wall. Below 3 nanometers, the physics break down. It becomes scientifically difficult and financially ruinous to manufacture. Then there is the geopolitical wall. The United States maintains strict export controls designed to prevent China from acquiring the extreme ultraviolet lithography machines required to print anything below 14 nanometers. The premise of this strategy is straightforward. Cut off access to the world's most advanced printing presses, and you starve the Chinese AI industry of the hardware it needs to operate. But this entire blockade relies on an assumption about how chips are made. What happens to that strategy if an adversary stops trying to shrink the chip and learns how to stack it instead? China's domestic semiconductor industry is adopting an engineering approach they call more than more. Rather than fighting physics and export controls to make individual transistors smaller, they are shifting focus to system-level integration. This is the mechanics of advanced 3D packaging. Engineers take multiple older, unrestricted 14-nanometer chips and stack them on top of one another, drilling microscopic vertical connections right through the silicon to link them together. Because these physical pathways are so short and dense, the assembled stack behaves exactly like a single, unified processor. It allows trailing-edge hardware to mimic the computational muscle of a heavily restricted leading-edge chip. But AI workloads create a unique bottleneck. These models require so much data that moving parameters back and forth between the processor core and standard memory banks takes more time and burns more power than the math itself. It creates a massive traffic jam. High bandwidth memory, or HBM, bypasses this traffic jam entirely. By physically layering DRAM chips directly on top of the compute architecture, the distance data has to travel collapses to mere micrometers. Chinese manufacturers like CXMT are now executing this at scale. They are currently shipping HBM3 memory samples directly to domestic AI developers, bypassing the foreign monopolies that usually control this supply. Mastering these vertical connections provides a domestic route for AI hardware that bypasses the need for restricted 7-nanometer or 5-nanometer fabrication. The primary corporate vehicle executing this advanced packaging strategy is a company called SJ Semiconductor. SJ Semiconductor is not a startup. It was deliberately spun off from SMIC, China's heavily sanctioned, state-backed national foundry. They are preparing for a $700 million IPO on the STAR market, and over 80% of that capital is earmarked exclusively for building a massive new 3D chip packaging facility. This facility is protected by a glaring regulatory loophole. Under international trade laws, advanced packaging equipment is classified as dual use. The exact same precision bonding tools required to stack high-performance AI accelerators are also used to assemble basic, everyday consumer electronics worldwide. Unilaterally banning the export of these packaging machines would effectively break the global electronics supply chain, paralyzing production for everyone. China is leveraging the legal access to these dual-use tools to scale a domestic assembly chain that existing trade restrictions struggle to reach. The U.S. Department of Commerce's Bureau of Industry and Security realizes this packaging loophole threatens to undermine their entire blockade strategy. In response, they recently issued a complex new set of guidance, specifically Red Flags 23 through 27, targeting the modification and assembly of chips after they have already been exported. They also implemented an aggressive update known as the Footnote 5 Foreign Direct Product Rule. Under this rule, the U.S. claims legal jurisdiction over any foreign-made item that contains even a single integrated circuit manufactured using American tools. This creates an absolute enforcement nightmare. Regulators are now tasked with trying to police the untraceable global movement of generic chiplets and standard bonding tools across thousands of supply chains. A regulatory framework originally built to choke off a few massive lithography machines is proving incompatible with a decentralized era defined by 3D chiplet assembly. Geopolitical strategists like Jacob Hellberg call this new reality Pax Silica, the idea that the 21st century global order is no longer underwritten by oil or steel, but by the compute stack. The technical frontier has expanded. Performance gains that once came solely from shrinking transistors now rely on the physical integration of the entire compute stack. While the U.S. strategy focuses on denying access to the smallest components, China is rapidly maturing the infrastructure needed to assemble larger ones. In the next decade of the AI race, control over the compute stock belongs to the engineers, who can most efficiently bridge the gap between processing and memory.